Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at the section 9.3 out of Giancopoulos, but this is a review of humidification, and you've seen this before. It was covered very well in Chem Eng 2100. That textbook probably has a much simpler, more straightforward explanation, in fact. We're going to go through very quickly some of the slides. I'm not going through the slides from that course here, but they are in the slide deck that you have in Canvas. I'm going to, in this video, look at what they do in Perry's Handbook, and then I've given you links to videos for my other course. So these are the basic definitions that are used in psychrometry or humidification. Now, in these cases, A is the moisture, so typically it's water. B is the moisture-free gas, typically air. And we're considering that these are at low pressures, modest temperatures, so nearly ideal gas conditions. We have absolute mass humidity, mole humidity, saturated humidity, relative humidity, percentage humidity, humid volume, humid heat, total enthalpy, dew point temperature, dry bulb temperature, wet bulb temperature, and adiabatic saturation temperature. The definitions are listed here, and the mathematical relationship for each one is listed here. Now for water, we're going to have lots of helpers to do this. Psychrometric charts are bound everywhere for those. But when we're doing this for a different system, not water and air, then these formulas become incredibly helpful to us. Perry's Handbook defines these in this way. If you're not familiar with Perry's Handbook, this is sort of the culmination of all things chemical engineering. It's edited and updated every couple of years. You can have a free version of this if you're a member of AICHE nationally. And so since that membership for students is free, you should definitely really consider doing that. You can look all of these things up. You can look up any topic that we're covering in our chemical engineering courses, and it is in this book. But these are their definitions that they use for these various things. Now notice that they use Y for humidity instead of H. But the verbal definitions and the mathematical definitions remain the same. Here is another excerpt from this. So volumetric humidity, vapor pressure, and saturated vapor pressure. More relative humidity. So you'll see these are the same things, but this is the way it's presented in Perry's Handbook. And this is something that you should probably have access to for the rest of your career. So familiarizing yourself with this is probably very wise. There's a table of formulas in the book that these are simplified for the system of air and water, valid to 3 significant figures. And so therefore, based on that, we end up with some simple formulas that relate pressure, mole fraction, humidity, temperature, etc. And this is another page of it, but this is going to be for a general system. So you'll see that there's molecular masses of your various compounds, either the liquid that is the vapor in the gas or the dry gas. And so these are the general formulas. And then finally, density and humid volume formulas for both the general systems and for water. Now let's look briefly at an example. On a particular day, the weatherman reports that the temperature is 46 degrees Fahrenheit, the dew point is 45 degrees Fahrenheit, the atmospheric pressure was 30.28 inches of mercury, and the relative humidity was 96%. And so based on this, just taken off of the Weather Channel actually, what's the mole fraction of water in the air? So we need to identify this information. So the 46 degrees Fahrenheit is what is known as the dry bulb temperature. This is just the standard temperature, the way we would normally measure it. We also have the dew point temperature is 45 degrees Fahrenheit. The pressure is given as 30.28 inches of mercury, and the relative humidity is 0.96. And they want us to find the mole fraction of water. So I've translated this given information to symbols. So now then we need to find definitions that relate these. What they gave us was relative humidity, so let's look up that formula. Okay, so this is the partial pressure of water, which is the same as Y of water times the total pressure, divided by the vapor pressure of water at the given temperature. Now this temperature is the dry bulb temperature. So I'm going to find this using either steam tables, an Antoine equation, something like that, but I need to find vapor pressure data. At 46 degrees Fahrenheit, I found that this is 0.1532 psia, or 0.3119 inches of mercury. Therefore, I can solve for Y of the water is the relative humidity, 96%, times the vapor pressure, divided by the total pressure. I want those units to cancel, so I selected appropriately. And so the mole fraction is 0.00989 moles of water per mole of dry air. Now the last thing I want to do is just briefly remind you of psychrometric charts. These are graphical representations of these most commonly used humidity-related quantities. T sub dB is the dry bulb temperature, which is the actual temperature. T sub WB is the wet bulb temperature, which is the saturation temperature. It is literally taken a thermometer, put it in like a wet sponge, let it come to equilibrium in the air, and what temperature do you read? So this is the saturated water temperature. When you have a relative humidity less than 100%, then the wet bulb temperature will be less than the dry bulb temperature. And as it says here, we can use a psychrometer to measure dry bulb and wet bulb temperature. And these are simpler these days than they were back in the days of sling psychrometers. This is the basic style of presenting this data. It's a psychrometric chart developed by someone named Grosvenor. And it has on here wet bulb and dry bulb temperatures. It has volumes. It has percent humidities, both absolute and relative humidity. And it has enthalpy and volume information. Most of the time we only see ones for air and water, but just so that you are aware that these things do exist, here's one, for example, for air and toluene taken out of Perry's Handbook. And the same information is contained here, just for a different system. So at this point, If you are ready to move on and use humidification to solve problems such as cooling tower problems, great. If not, go back and review some of the video lessons taken from our mass and energy balance class. At this time, I'm going to conclude, so thank you very much for your time.